not the least of which would be things like provisions for the crew, the amount of water that would be required. We thought his ascent vehicle was very large, which meant his power requirements, his propellant requirements were much larger than needed to be.
Weaver took Zubrin into his office, and the two men worked out compromise mission architecture. First, Weaver wanted 3 launches for every mission instead of 2. The first year, 3 ships would launch: a MAV, Mars Ascent Vehicle, an unoccupied HAB with extra supplies, and an ERV, Earth Return Vehicle. The HAB and MAV would land on the surface and begin producing fuel for the return flight and air for the crew. These craft would spend 2 solitary years on Mars, allowing NASA to test all of the systems before sending a human crew. Then, in the 3rd year, 3 more ships would launch, this time with the HAB occupied by astronauts. The other 2 ships are for a future mission, and less needed as a backup for this crew. Once on Mars, the team could also utilize the first HAB. Then, after a 1.5-year stay, the crew would climb aboard their small capsule, blast off, and rendezvous with the return ship. This ship would carry them back home in a roomier environment than Zubrin's ERV. Zubrin called the plan Mars Semi-Direct. NASA called it the Design Reference Mission. The plan was subjected to the same cost analysis that tagged the 90-day report with a $450 billion price tag. The Design Reference Mission came back at a fraction of the cost, $55 billion. Spread out over 10 years, it could be done within NASA's existing budget. The plan made the cover of Newsweek. Here was a mission architecture that was affordable and could be done today with existing technology. But NASA's astronauts have not left low Earth orbit since. In the wake of the Columbia tragedy, a debate has raged over the future of space exploration. Should NASA continue to focus on low Earth orbit, developing technologies for the future? Or should NASA have a goal, like it did in the 1960s with Apollo?
Without the presence of a driving imperative, we engage in basically a random set of constituency-driven programs which are justified ad hoc afterwards by the argument that they could prove useful at some time in the future when you actually have a plan to go somewhere. The American space program's been stagnant for 30 years. There's a once-in-a-generation shot right now to get it moving again by giving it a goal that'll take it somewhere. So the stakes today are high. And if you ask me if I am nervous right now, I am.
Dr. Zubrin.
Why is NASA stuck in low Earth orbit? The problem with NASA's lack of current achievement is not money. The problem is lack of focus, it's lack of a goal. It shouldn't be humans to Mars in 50 years. It should be humans to Mars in 10. We can do this. We do not need gigantic nuclear electric spaceships to send people to Mars. That is pork, it's nonsense. The primary question I get from the American people is, why aren't we doing this? There's a big sense of disappointment, almost verging on a sense of betrayal. The purpose of spaceships is to actually travel across space and go to new worlds, not to hang out in space and observe the health effects from doing so.
Dr. Zubrin, in your testimony, you were very passionate, but you also were mad. You're mad we haven't done this, or that this vision has been stolen from a generation?
I guess you could say that. It's like Columbus coming back from the New World and Ferdinand and Isabella saying, so what, forget it, burn the ships. Okay, you know, that's what has happened in this country. We've won our point that there needs to be a destination. What we need, the point we need to win on now is that the destination needs to be Mars, and it needs to be soon.
Like the Apollo missions to the Moon, sending human beings to Mars will mean putting people in harm's way. There are many dangers in outer space, and many things could go wrong. A serious equipment breakdown could doom the crew to their deaths. Some argue that the risk of failure is simply too high.
You know, back in the days when medieval man was looking out from Europe and thinking about exploring the world was unknown, and map makers populated their maps with dragons. We've got the same thing today. There are people who are afraid to go out into space, and they've populated their maps of the solar system with dragons. But these are dragons that we can take on.
There are two kinds of radiation astronauts must contend with in outer space: solar flares and cosmic rays. Solar flares are floods of protons that burst from the sun at irregular intervals and would be dangerous to an unshielded human crew.
We are not ready to send humans to Mars right now. We've got to know a lot more about radiation and radiation mitigation. One of the Apollo flights barely missed, like by a week, a major solar event. If it had gone off when the Apollo astronauts were on the way back and forth to the moon, they would have gotten their entire lifetime radiation dose in that one mission. And that's just one solar flare. So that's why we worry about this.
In the Mars Direct plan, Zubin envisions a central insulated core where a crew can retreat to while the radiation passes by. The core would be surrounded on the lower level by all the provisions of the mission. This should stop any harmful dose of radiation from reaching the astronauts. Fortunately, solar flares are predictable, and the crew could be forewarned by astronomers on Earth.
Basically, you use your pantry as your storm shelter. So a solar flare happens, the alarm bell rings, the crew goes into the storm shelter, they stay in there cramped up pretty tight for a few hours until the all clear rings and they come out. This is going to happen once, it might happen twice in the course of the mission.
The second type of radiation is cosmic rays. This constant rain of charged particles comes from interstellar space and cannot be avoided without many meters of shielding. We can experience some of this type of radiation on Earth at high altitudes. Airline pilots who spend their careers flying high in the atmosphere can receive almost as much of this radiation throughout their life as a Mars astronaut would on a 2.5-year mission. Over short periods of exposure, cosmic rays are not a great concern, but over longer periods they could prove unhealthful.
It's a long trip. It's a 6-month trip there, a 6-month trip back. It's probably a year on the surface. That's a lot of radiation.
The best estimates are that the magnitude of that dose that you would get in the 2.5-year round-trip mission is not that great. Perhaps 60 rem of radiation scattered over 2.5 years. Now, 60 rem of radiation delivered over a long period of time like that would not create any noticeable effects at all. It would, though it is believed, increase your statistical risk of getting cancer at some point later in your life by about 1%.
With the immense distance from Earth, never before experienced by a human being, with the constant dangers of outer space surrounding their small, life-sustaining craft, and with nowhere else to go, the psychological impact on a crew could be severe.
Fear is real. I mean, it would be, to me, abnormal for a person to not feel the fear of getting on a rocket and launching into space and going to Mars. So I think fear is a very normal thing that all astronauts, in fact, are supposed to have. And I would be afraid to fly with someone who does not have fear.
Some psychologists worry that cabin fever could set in, and the crew might literally go crazy.